So to start off with, we want your data. So you've got your volume and pH data entered in. So what we'll go through and do first is find how to insert a chart. The chart you want, stupid Excel, you want a scatter chart. I would pick the mark scatter. As far as getting the data in, now select your data, add series, name, why not? X values will be your volume because it's the independent variable. Your Y values will be the pH. Okay? Should be set, and there you go. There's your data. Looks beautiful. So things that I would do, first off, make it bigger so you can see it. Other things as far as turning in and submitting for your report, you need to make sure that your table has axis labels. So this one would be volume, if I can spell right, in milliliters. Your other axis, I prefer the rotated title, but that's up to you. This would be pH. Okay. So after this, we said the whole clutch of all of your experiment was coming off of determining your equivalence point. Well, your equivalence point is right in the middle of where your pH spikes. Okay? So if we look at your data, what we're saying is right about here. Okay. So what we could then go through and do is say that's the equivalence point, and this is one method for determining it. We kind of do, in theory, a straight line down. This is your equivalence. How do you spell equivalence? Yeah, I was close. You've got your equivalence, I would call it volume in this case. So at that volume, we could then go through and do all our other calculations. So we could use that volume to get to ultimately our molecular weight for the compound. If we take half of that volume, so in this case, we're guesstimating at roughly 22.5 milliliters. Half of that volume would be 11 point something. So right about here, we could then, come on, draw a dashed line. Go up to the curve. At that point, if we go to our Henderson Hasselbalch equation, pH equals pKa, was it plus log A minus? Anybody remember? I have to drive it each time. I think it's A minus over HA. It's not going to matter in this case. At that point, A minus equals HA, which means this term cancels out. The pH equals our pKa, so now we can draw a nice little line over the other side, and your pKa is roughly, what is that, 4.2, 4.3. Okay, so that's a good approximation. In theory, you would know what your answer is supposed to be because you asked me for what it was. I don't think anybody in this class has asked me for what it was. That's because I forgot to tell you that you needed to ask me for what it was. So you need to get that information from me, what your pKa value is supposed to be and what your molecular weight is supposed to be. I have all of that information somewhere, so I can tell you based on what your unknown is, what your pKa is supposed to be, what your molecular weight is supposed to be. So that way, when you write up your discussion and conclusion, you now have something to discuss. Were you close? Were you not? Okay? So that method kind of works. You'll notice, at least the way I've got it drawn, there's all sorts of weird dashed lines, not very straight, not very accurate. Okay? So ideally what we would do is make this a little bit cleaner. So what I'm going to do is adjust this so that we can see this a little bit better. I'm also going to change the chart type. Oh, I need to escape. Change the chart type real quickly. really. I want some connected lines in between them. And what I'm going to do is zoom in on this tiny little section right here. Okay? So that I can see that a lot better. So I'm going to set the format the axis. This is a bit painful in Excel, but it works. To be minimum of a pH unit of 7 and a maximum of 10.5. Okay. We know your equivalence point is somewhere in that range. We said roughly halfway between the only 2 points there, so that's what we'll work with. So now what I'll do is change my x-axis. This is a very silly way to do this, but it works. 22.5 is the minimum. Go too far? No. And we'll make the maximum 23. So now I can see that line a lot better. Okay. I'm also going to increase or decrease the major unit size so I can get a little bit more accurate. Whoops, too much. A little bit more accuracy in the number that I pull off of it. So now when I do OK, where I'm kind of dead center, I would approximate in here. This is ultimately a fancy way of guessing, just so you know. Nope, I didn't want that. Do a straight line. I'm going to say right about there is halfway in between. Can you see the cursor up there?
Yeah.
So where do you want to go? There? Does that look like halfway? This is officially your data, so you get to decide. Yeah? Okay, so we'll draw as straight a line as I can, straight down. That now crosses my axis at 22.718. That is now the equivalence volume. Okay, that is one way for estimating it. So that is literally just estimating it with what the data we've got. Not the best method, but it'll work. Once we've got the equivalence volume, half of that gets us to our half equivalence point. So what did we say the number was? 22.71 divided by 2. The next point I want to get to would be roughly 11.35 to get my half equivalence. So we'll now format the axis again. Minimum, I'll go 11, maximum 12. Major unit, we'll make substantially larger, there we go. Yes, that will work. In that range, the pH was, so we go back to our data, the pH is roughly 4. So the minimum value I'll do would be 4, and the maximum, let's say 4. Well, I'm going to say 5. Okay. As far as my minor units, I want to get as much data as I can off of that axis. So I'm going to make the minor unit, the major unit, but it's easier. Try 0.5. That should work. Say OK. Our half equivalence is our 11.35, so I'll shift that over to just a hair over the 11.35. Extend that straight upwards. At that value, where my line crosses your data, is the pH range we need to get. So I will draw yet another line. I'll be right there. So we'll now shift this up at that crossing point. So now where it crosses our y-axis is the pH. So 4.71. 0.72, that would be the pH at the half equivalence point. Okay? So that was done just by manipulating the graph, looking at it in different positions, and really just looking at it. So we're really estimating a lot of stuff here, which means we get massive amounts of error. Okay? So what we'll do next is first off delete all of that. Let's get it back to our what we want this to look like. So we'll format the axis. We'll let Excel do whatever auto units it wants. Make those all auto. We'll go back to the data, and now what we're going to do is shift to the lab procedure in just a second and calculate some extra stuff. Now what we'll go through and do is the two mathematical versions for this, and I might need some help remembering some of these things.
You're recording, right?
I am recording, yeah. So our procedure gives us the option of doing these two extra plots. So everything we've done so far is just guessing approximately where things are, which isn't very good. Okay, so what we want to do is come up, I don't know what I said, let's just run with it. It might sound a little choppy, oh well. So first derivative plot. So to get, before we do that, let's take a look closer at our, no, it's Excel. So when we look at this graph, what we're trying to get is the point right here. Okay. For those of you that are in calculus or have taken calculus, that point is known as the inflection point. It's where we shift from having our curve, in this case, facing upwards, versus our curve after that point facing downwards. Okay.
Concave down.
Concave up versus concave down. Okay. Mathematically, what we can do is go through and calculate the slope at that point. Well, in theory, what is the slope where we switch from concave up to concave down?
0, 90.
Change in y over the change in x. The change in y, it ends up being infinite because our change in x is 0, right? Did I do that right? Yeah, because the distance, our change in x is so small, and we get a massive change in y. So we get a large change in y over a very small change in x. That gives us an infinite value. So what we can do is go through and plot the first derivative. And then when we plot the first derivative, we can look for the point where our peak of our data. Okay, that peak is going to be where our slope is infinite, or where our initial slope was infinite. So that would be our first derivative plot. We can also run a second derivative plot. When we run the second derivative plot, it's the slope of our first derivative. The slope of our first derivative at the peak is a flat line. Now we have a 0 slope. So our first derivative plot, we'd pick the point where it's maximum, where our data is maximum. Our second derivative will be where it crosses the x-axis. So depending on what you want to work with, you may get easier numbers versus others. So it's going to depend on what your data ends up looking like. Okay, and that's what, that is what your lab procedure is trying to tell you. Okay, your first derivative versus second derivative plots. Okay, what is a derivative? Those of you, anybody have taken calculus in here?
If it's like x squared, then you just do 2x.
Okay, that's mathematically solving for what does it graphically represent.
So this one is the volume?
The slope.
There it is.
Yeah,
it's the
that's
slope of the line. So it's the change in y over the change in x. Okay, so if we go through, what was our y value for our graph? pH. So what we want to do to get our first derivative plot is run the change in pH over the change in our volume versus the volume. Okay? What this will do is relate our slope to our volume such that when we see the peak, that's our equivalence point volume. If we do the second derivative, it's then going to be the slope of our first derivative plot. So it's the change in the change of the pH with respect to the change in the volume over the change in volume. Okay? So what we're going to end up doing is running calculations to get that done. Okay, it may sound a bit hectic, but the calculations actually aren't too bad. Okay, so let's go through back to our results to see what's happening with those. Excel. So what we're going to do is create a new column, and that new column, I'm going to call this first derivative. Okay. To get the first derivative, we said that it was, I'm going to shift down one cell, is equal to the change in the pH. So the change in the pH here was 4.09 minus where it started, divided by the change in volume. I need to make sure I include parentheses on this. Divided by the change in volume across that same range. Final, initial. I now have my change in volume. Okay, yes, no? Or sorry, my slope at that line. So that was the change in pH divided by the change in volume. I want to do that now for all of these possible options. So I can now click and drag. I think if I go one too many, it's not going to work. Let's take a look. This refers back to, yeah, that data point's useless. So we'll go ahead and delete that. We have to be a little bit careful when we plot our volume, so we'll call this first volume. That was the slope of the line, so if we go back to our initial data, our things calculated here for our first derivative, was the slope of the line at what point? At what volume was that accurate? I mean, it wasn't our initial volume, it wasn't our final volume. We're really saying that that's the slope of the line in the middle of those. Okay. So in that case, it would be roughly 3. What we're going to do is take the average of those two volumes. Okay. So we can go in, it's a bit silly to do it this way, but I'm going to do it this way anyway, equals the average of the two data points of our volume, 3.5. Okay, and if this is done right, the average of 5 and 6.2 is 5.6. Looks like it worked correctly. Okay. It's a very subtle difference, but you should be accounting for that different volume because we are looking at that average. Okay, so you should account for that when we go through and do this. Okay. Now what I'm going to do, sorry, this might make you sick if you watch it too carefully, is shift the titration curve out of the way because I want to be able to look at my first derivative curve. We still want to go through and insert a chart. We're going to do the scatter, and I think I like having the lines in there, so we'll do the straight marked scatter. Okay. The data we're going to select this time would be for our first derivative. So we can do select data. We'll add a series. I'll call this series first derivative for the sake of being able to go through and identify things. Okay. On the y-axis, or sorry, the x-axis is our independent axis, which is going to be our volume still. Okay. But it's going to be our first derivative volume. Remember, we had to take that average issue. Okay. So we'll run that as our x-axis. Our y-axis, assuming I did everything right, we'll see here in a second, we want to be plotted the numbers. Will be our first derivative plots. So we'll select that. And if I did everything correctly, when we click OK, I'm a little bit nervous about this. When we click OK, what we should see underneath on our graph will be essentially a flat line that all of a sudden spikes and then comes back down and flat lines on the other side, and we get a single peak. Hallelujah. That means we did it right. Okay? So our equivalence point is at that peak. Okay? Since it's not particularly easy to see that peak right now, what I would again do is zoom in on it, just as we did before. I forgot how I did that. Format axis. So for my x-axis, I'm going to do minimum value of 21.0 for this. Hey, that worked. Up to let's go ahead and say 24. Okay, and now I can see that curve. Okay, this is where it's going to get a little bit tricky as far as deciding what value should we use. Okay, in theory, so we can scroll over that point, but that's assuming that you hit it exactly on. Okay, so really what Excel is showing you is not the fit of all of your data, but the average of everything there. And so what our curve is actually doing, what our curve is actually doing is something along these lines. It's staying flat until it sharply goes up and then comes back down. So that peak value is now the tricky question. Is it indeed this peak, or is it some value that's actually over in here? That looks really awful. Let me try and zoom in and redraw. Okay. Where is our peak? This is definitely still going up. This is definitely still going up. Does this go up to that peak in actuality, or is that a figment of our data? Okay. It's probably a figment of the data. Okay. So we don't necessarily know where our equivalence point is going to be exactly. Okay. For sure, it is somewhere between this point and this point. Okay. So what you could go through and do is say it's probably closer to this one, because that's the taller peak. Okay, and we would assume this one is just a weird signal. And we could say that the volume at our equivalence point is probably 22 point, it's probably a little bit less than that 0.7, so 22 point, let's say 65. Okay, can I get away with that? And we'll get rid of all of that. And give me my cursor back. Yeah, 22.6 or 65. Okay. What did we say based on the estimation? Theory, you wrote that down. So when we just looked at the graph, what did we say our equivalence point was? 22.7 versus 22.65. Okay, our estimation based on zooming in was pretty darn accurate. Okay, so it makes sense. We're getting these two sets of data, or two different methods, to actually overlap. Good deal. Okay. Since we still aren't 100% positive, we're still estimating where that peak is. What we can go ahead and do is now run the second derivative plot. Okay? Our second derivative plot is the slope of our first derivative plot. So it's the change in that y versus the change in x. Okay? So to go through and do that, again, sorry if this makes you sick because I shifted around. Get that graph out of the way. I want to now generate the second derivative. So I'll enter a new column for second derivative. And because, again, since I'm taking an average across that distance, I'm going to do an average volume too. So I'll do a second volume. Okay. So the second derivative, we'll shift down further, is going to be the change in y. So our first derivative final minus our first derivative initial divided by our volume final. Whoops, sorry, I need the parentheses. Our volume final minus our volume initial to get us that slope. Okay, I'm going to hit return. You'll notice it's negative. That's okay. Don't stress about that. We'll click and drag down to generate all of that data. Okay. When we go to get our second volume, that we have to again realize that we're doing again an average for our slope, so we should go through and again do the average for whatever the data point was, whatever volume change it was. Click and drag to propagate all that data out. Okay. To get an idea of what's happening, we're again calculating the slope. Okay. What are we looking for? Our goal is to get the value for this peak. Okay. So if we go through and do a second derivative plot, we're looking at the slope along this whole graph. So what's the slope to start with? What's our change in y to begin with? So where I've got highlighted in orange over here. how much does the y value change?
0.
Doesn't change. Okay? Then all of a sudden, what happens to the slope?
It's positive.
It goes positive. Okay, what happens on the back end? So let's work backwards now. The very end of our reaction, where's our slope?
So 0.
0, but then it goes. Remember, our positive negatives is always left to right. The slope of this new line here is negative. So what we're looking at is to get the peak is going to be where our slope goes from positive to negative. Where are we going to see that transition? What would the slope of the line be where we transition from negative to positive? Start at -2, and I want you to get to +2. Where do we transition from it being negative and positive? 0. So the second derivative plot will be nice because where we see our slope or our line, our graph, go through the x-axis is our equivalence point. Okay? So we don't have to do any weird interpretations of any of the data. It's exactly where it crosses the axis. Okay? So that's a little bit easier to see and visualize. At least that will be the hope. So what we'll go ahead and do is take a look at that graph. So we'll move the first derivative out of the way.
What would you enter for second derivative again?
So the second derivative, just like the first derivative, is the slope for our second derivative column, but it's the slope of our first derivative. So the values that I've got here are the change in y for my first derivative column.
That's what I thought I did, but I didn't get negative.
Because the slope is so small, you may not get a negative or positive there. Because in theory, it's supposed to be 0. So it'll be something very, very close to 0. And if you look at all those values, they're all really, really, really close to 0 until it starts to spike, and then it really rapidly shifts the other direction. So when we look at your graph may not be negative to begin with, but it will be something very close to 0. Okay, so when we go through to plot it, I'll take a look at it, and if your plot doesn't look like what we're about to see, then that's something we'll take a closer look at. Okay, so we will go through, select data, add our series. We want our second derivative. Our x values are our volume. Our y values are the slope of our first derivative, so our second derivative plot. So now when we go through and click OK, we should see a flat line, a spike, that there very rapidly drops across the x-axis and goes back to a flat line. Okay? So let's see, did I do it right? There we go. We get a flat line with virtually no intensity, so a 0, with a very quick spike upwards, and now a spike negative, and then back to the flat line. And that represents what's happening as we are measuring the slope of an initial peak. Okay? Not particularly easy to see that, so what we'll do again is zoom in where we want to. Okay? We want to see where it crosses the x-axis. We already have an idea of where it's going to cross. Where's that idea? It's about 22.7. Okay? So we'll make our minimum, zoom in really close, 25. Our maximum, I'll do 27.5. Oh, and why that's not easy, I think I might have my minimum and maximums too big. Let's make the minimum -10. Why can I not see it? Okay, let me back out of this, see if I can figure out what I did wrong here. Let's change our minimum, zoom in a little bit more slowly. 20 to 25. What did we say our equivalence point was? Oh, that was a problem. I did 25. That's why we couldn't see anything. Helps if you zoom in the correct area. Okay, so At least I think that's what I did. So we'll change this again so we can zoom in a little bit better. I'll make this 21.5 to 23.5. And actually, I'll go back to that axis again and add some more detail into it. We'll make our major units every 0.1. Let me read that okay. I'm going to zoom in even more. 22. 23.5. Whoa, let's not get that close. 8. There we go. So now we've kind of zoomed in at the best we can. We can change the y-axis a little bit so we can see this a little bit cleaner. Let's do our minimum. Let's just make them 40s. Remember, you may be adjusting it depending on what your data is. Okay? We want where it does the sharpest change across the x-axis. So this little blip here is likely just an experimental error. Okay, so we won't worry about that. So what we'll look at is that exact point in here. Excel is giving me, so ignore the little box that's popping up because it's not going to give us the exact value. So if we go back and look at this, so 22.64 is one hash mark, the other one is 22.72. So we're looking at some point exactly in between there. Depending on how many sig figs you're really going to drop in on that, it's going to depend how zoomed in you want to get. For me, I would approximate that at, it's a good thing I picked nice round numbers to show this. 22 point, I'd probably stick with 22.70. I mean, that's pretty close to what I would see. So what we're looking at is trying to get this value right there. Okay, exactly where it crosses. And we said to ignore this one because that's likely experimental error. Okay? So your equivalence point based on your second derivative plot is 22.70 for your case. That is the volume necessary to get to that point. Okay? So once we've got that volume, we can now go through and do some calculations. Okay? You guys have any questions about how we got these plots? Pause that real quickly. Okay, so as far as your report goes, you should end up with at least 3 graphs. You should have, I have to organize these. You should have, you should have your pH titration, which you can include as is. Make sure you've got the axis labels and the figure descriptions telling me what it shows. Okay. After that, you will then end up showing me the first derivative plot. If you zoom all the way out to your initial, what you initially looked at, I'm not going to be able to interpret that worth anything. So try and get it zoomed in so that you can at least get an idea of what peak or where the peak is. So with the data that we're looking at right now, I would say this first derivative plot looks perfect. That's exactly what I would want to see. Okay. Again, axis labels and a description. You'd then go through with the second derivative. I do want it zoomed in, but not this much. I'd like to see a little bit more detail on that. So what we can do is change this. Let's try 60. Let's try 80. There we go. And 80. So now I can see it peaking and going down. The x-axis, I want to zoom out a little bit more on too. Who's more on? Oh, sorry. Hopefully I said that quietly enough, no one heard. So, and change the axis. units so that that actually looks reasonable. Okay, change it again. Let's just make that one. That way for sure it'll work. This way I can see that you've zoomed in the appropriate area. I can see everything that has to do with your graph. I now know roughly how you're interpreting it. Okay? In each of your descriptions, you should provide what the equivalence point is based on that graph. Okay? And as we've seen, each of your equivalence points for each of these is roughly the same. If it's not roughly the same, you did some calculation mistake somewhere. Okay? They should be really, really close to each other. Okay? At this point, you've now done all the graphical analysis you can do. You would shift into the calculations. So of these three graphs, pick whatever value you want as your equivalence point. That is the value you will then go through and do your calculations with, okay? Which we will now attempt to go through and show. So since we're using your data, we'd start off with, let's not do color, equivalence point from, what are you going to use? Second derivative? First derivative? Second derivative plot was what? 22.7. Oh man. 22.7 milliliters of NaOH. I'm going to add here, I do want to see one more sig fig. Okay. And if you're happy with it being a 0, I'm fine with that too. Just make sure that that sig fig shows up for your equivalence point. Okay. Now you could go through and do your calculations from this. So we had kind of two ways or two things to do. So I'm going to attempt to squeeze it all in on the same slide so we can get everything fit. Roughly halfway in between. We've got your, again, just trying to fit, the molecular weight calculation. This comes from, sorry, from the equivalence point. Okay. To start this calculation off, I would go with HA, which represents your weak monoprotic acid, plus NaOH. I would actually shorten that, get rid of the Na. Just do OH minus, goes to A minus plus H plus. Because this is a strong base titration, we don't have to do any kind of weird ice charts or anything goofy like that. We won't have to do any ice charts for any of this. Okay? But it is a standard kind of limiting reagent calculation. So what we know of HA, come on. Fine. For HA, we know the mass. So do you have your calculations or your results for your mass? What we're now going to do is just include all the information we know for these. It was 0. For the unknown. Should have been 0.4 or something. 3915? 15 grams, so that's happened to be what this group weighed out. We don't know anything else about the acid. As far as the base goes, we know its molarity. Did you already calculate the molarity? You did your standardizations. You got your 4 standardizations, so you should show those calculations to get that and your average molarity from that, which should have been close to 0.14. Anybody remember what it was? I think it's for the base.
The base was 0.7 grams.
Not grams. No. That's KHP. I want to know the molarity of your base solution. You were supposed to.
0.1.
Yeah, okay. So it's roughly 0.1 molar. That value, I guess I'll highlight that as a different color because You need to determine that. You'll need to show me the calculations for how you determine that molarity, but it should be close to 0.1. That's all the KHP, titrations, all that fun stuff. So that would be before we even got into these equivalence point calculations. Okay. We also know the volume of base added. Okay. How do we know the volume of base added?
Version of 0.7
This was the molecular weight calculation from the equivalence point. What was the equivalence point? How much base you added. Okay, so how much base did you decide was your equivalence point? I already forgot it. 70 milliliters. So now what we can go through and do, because it's a limiting reagent type calculation, is we can convert or find the relationship between the moles of base to the moles of acid. Okay, so the moles of acid are related to our moles of base. To get the moles of base, we took 22.70 milliliters, writing way too big. So I'm going to have to break this into multiple steps. Sorry, let me erase all that. We'll do our moles of base equals the volume of base that we added, which was 22.7 milliliters, times its molar mass, so 0.1 moles per liter. Notice the liters don't cancel out, so we've got to do our unit conversion. 1 liter is 1,000 milliliters. This gives us our moles of base. What's the relationship between our moles of base to the moles of acid? I don't quite accept the same. It's 1 to 1. 1 mole of base is 1 mole of acid. Okay? And we got that from the balanced equation. Okay, so our moles of acid is equal to our moles of base times our mole-mole conversion. I would hope to see this conversion in all of your units and your calculations and your work. More than likely you'll leave it out. Not that big of a deal one way or another. That tells us the moles of acid. We wanted to know the molecular weight. Molecular weight is grams per mole. What did we just calculate? The moles of the acid. Do we know the grams of acid that were put into that moles? Yeah, that was what we weighed out. So in this case, that was the 0.3915 grams. This should give you the molecular weight. Okay. For your discussion and conclusion, for those of you that are actually here, you can give me your unknown number and I will tell you what your molecular weight should be. Okay? That way when you get to your discussion and conclusion, you can then compare what you calculated to what you actually should have gotten. Okay? So you've got something to actually discuss. Okay? So that's your molecular weight calculation. As far as the Ka calculation goes, okay, so to get our Ka, the Ka is going to come from the half equivalence point. Okay, and this is all graphical interpretation now. So what do you know at the half equivalence point? We know from the Henderson Hasselbalch equation that the pH will equal the pKa because A minus will equal HA. Those concentrations equal each other, which means that log term drops out and we now know our pKa. So what we've got to do is figure out the pH at the half equivalence point. So what was your half equivalence point? 1/2 of what your equivalence point was. So your half equivalence, you already just told me, it is equal to, what did we say your equivalence was? 22.70 divided by 2. Your half equivalence volume was, sorry, you said 11.35 milliliters. To determine your pH at that value, you'd have to do that graphically. So you'd go back to your pH graph, your pH titration. So now we'll go do graphical analysis. Sorry, I thought we were done with the graphical analysis. At volume equals 11.35. Estimate your pH as accurately as you can. From the Henderson-Hasselbalch equation, we know that the pH equals the pKa at that point and at that point alone. If we want the pKa, the Ka value, what do we need to do? 10 to the negative pH. Because remember, to solve for the p anything, it's the negative log. So if we know the pKa, we can get our Ka. Okay? Because we are estimating the pH at the half equivalence point off the graph, I do expect to see that show up in your description for the pH titration. Okay? Because that information is coming from that graph. So you should flag it and star it and say, hey, this is the value. Okay? So the one calculation I didn't walk through was your molarity calculation. You should be able to do that without my help. Ideally, you put that into a table with the molarities from each trial, and then tell me what the average trial is. Okay? That would then ultimately be pretty much the rest of your report, your discussion and conclusion. Once you get your molecular weight and Ka from me, you can then compare your result to that actual and say whether it was good or bad. If it's bad, you need to explain why. If it's good, you should still explain why. Okay? You minimized error, there weren't a lot of places, it's all based on the instrument. Titrations, you're a robot now when it comes to titrations, and it's super, super easy. Okay? So your discussion and conclusion probably won't be that long. Okay? Questions about any of that?